Okay, I'm back, guys. I guess maybe I should have waited for the song to finish. Oh no, it's like in the middle. It's okay. Right, so I generated this graph, which is great. So essentially, I fixed the problem that we were seeing earlier where we weren't able to generate the histogram in parallel. This kind of sort of proves that, look, we're off by one somewhere. I don't know how we're off by one, but we're definitely off by one. The orange is what we're supposed to get. The blue is what we do get. And so we're essentially one element behind. That's fine. We just have to fix the off by one error, and then we're essentially good to go. I'm not entirely sure where the off by one error comes from, but that's okay. We'll figure it out, and we'll just kind of, if you work on it. I think it's because this min element needs to have a -1 in there. I think. Because the min element will be 1. Yeah, so let's go ahead and do that now. We're going to do include. Then we're going to do histogram plot, histogram k out here. And now let's just go ahead and plot histogram k out. And now we see that, yes, we see that the green curve is overwhelming the orange curve, so we have something that is working on the CPU. Let's see if it works on the GPU as well. So we're going to do coup array of input here. Please don't break. And then if that works, then we're good to go. What happened? For those of you guys who may not be aware, I have been trying to get this histogram to work for the past like 3 weeks. It's super simple. There's absolutely nothing crazy happening. It's just that it's taken me a while. I think I can remove everything after this. See what happens. Give it a second to finish the run. It's apparently taking a while, which is fine. Yeah, give it a second. Let me get some water. Where did I put it? Up here. All right. It's all zeros. Wonderful. Okay. Well, that was not what I expected at all. Why is it all zeros? So, did it output it appropriately to a coup array? Or not? It says it's a 128 element of int64. Let me check. So let me try running this. So what this is going to do is it's going to create a histogram input, and then it's going to run the histogram tag on the coup array of output, and then we wait on the event to finish. So there could just be something weird going on here, where we are using the wrong value. So what we might want to do is the following. You might want to return histogram, create this here. So let's go ahead and yank and paste in here. DD there, yank and paste here, and we're going to say coup array here, and then we're going to return histogram output, yank and paste up here, and up here, DD, and then we don't have to run coup array of a coup array, we should just be able to run histogram output there. Write this, go over here, include one more time. Try running it one more time. Okay, so now we get a 128 element coup array, which is great. Now, what you'll notice is this coup array is remarkably different than the other ones, and we'll talk about exactly why that is now. So let's do plot histogram k out. Let's just run this as an array. And right, so you'll see here that the purple curve is way different. And this is because we have not, at this point in time, dealt with conflicts, warp level conflicts. And such like this. So we'll deal with that in just a bit. As long as we have the CPU version kind of working, I'm relatively happy with where we're at. So I'm going to go ahead and clean this up a little bit, then commit it. There's actually some stuff being printed out that I don't want printed out. So let's go ahead and not print that out. And that should be here. Write that. Oh man, my contact is messing up. I hate it. But yeah, so let me go over here really quick as well. Again, if you guys have any comments, questions, concerns, ideas, anything like that, feel free to let me know. So, right, so what happened was I took an hour-long break. I know, look, that's awful for Twitch. I realize it's awful for Twitch. But the fact is, this particular month is not about, doing long Twitch streams. It's not about, getting YouTube content. Well, it's not about, doing super long Twitch streams. It's about getting work done. And the fact is sometimes stream is super helpful for getting work done. Sometimes it's not helpful at all. So, this was one of those cases where a stream was definitely hurting me, not helping me. So I said, okay, let me take an hour break and get this fixed, and I got it fixed. So now we're moving on to the next thing. Good. Okay, so we have a semi-working stuff. So let's see. So let me take a look at the to-dos here. This is a 1D histogram for n-dimensional binning. We need to think a bit more. The problem here is that at synchronized calls only synchronize across blocks. I think we need to find a way to do a coalesce write to global memory. Okay, I think this is done. I don't think we need to think about S vectors, but maybe I'll leave that in. That's fixed. LID doesn't make sense on the CPU as we only use 4 cores. It's still fine. It doesn't make too much sense, but it's fine. Make sure we use LID instead of TID for the histogram at the end. This is done. So the only thing we have to do is think about this as well is also done. So the only thing we have to do is think about S vectors. That's the only thing left to do. So I think actually we don't even have to put that down. I need to go do my job. Be safe. Hey, Nick. See you, Nick. Thanks for coming in. Sorry, I realized that I just hopped in. Also, thanks so much for the resubscription for 1 month. Let's go ahead and put down Simul Cow. I didn't realize you'd only been subscribed for a month, but thank you for all the support. Really appreciate it. But yeah, so the other thing I was going to say is that, is it only 1 month? Huh. Oh, 6 months. I'm an idiot. I misread it. I was like, I was sure you were subscribed for longer than that. Let me put 6 more in there because I'm an idiot. Sorry, 1 second. Let's grab this. 2, 3, 4, 5, 6. There you go. That's 6 Simul Cows. Thank you so much for coming in and for the subscription and all the support. I actually think since we have something kind of sort of working, I'm going to go ahead and commit what we have, and then we're going to do some algorithm archive PRs after that. In fact, let me go ahead and change the title of the stream to be more in line with what we're actually doing for the next few, maybe hour. I don't know. We're just going to do some algorithm archive PRs. So let's go here and work on that. So let's do histogram algorithms. Okay. Misfilled algorithms. Perfect. 1 second. There we go. I must stay for the algorithm archive. Wait. I don't know how long we're going to do. So I know there's a few that we can quickly merge, and then there's one chapter that I have to update. And I'm not entirely sure how that's going to go. So let's go here and let's just see what we can do. So first we're going to go to GitHub and then go to the algorithm archivists. And I know there's a few that I can just quickly merge. I know there are a few. And then a lot of dev container stuff, which let's see what we have here. So I think, yep. So Nick has been assigned for all of these. That's totally fine. Also, take your time with them. Don't worry about it. Implement stack and queue and go. Monte Carlo and Crystal. There were a few of these that were ready to go. I remember seeing the notifications, but I don't remember where they were. Let me go back and just check the very end. Euclidean proof. Let's see what we got there. Cryptography, insertion, sort, chapter. Let's see what we have for these guys. It's been a long time since we looked at these. I don't know what to do with that. That's okay. Let's go down. I don't even know what to do about these either. Okay, we're gonna do chapter reviews in a bit. Let's go to page 2. Okay, page 1. Now again, I know there were a few that we could just quickly merge. I just don't remember which ones they were. It might have been this one. Okay, let's see what do we have here. It looks like I think this one's already been reviewed, so I think this one's probably good to go. I'll ping Nickel V's here. I'm just gonna comment on here. So what do you guys think? Let's go ahead and comment there. Okay, I know there was one in here. I don't remember which one. Haskell Barnsley Fern. I think that's the one I was just looking at. C# implementation for the approximate counting algorithm. This is I like the fact that there has been added documentation in each method, but I'm wondering if XML docstrings wasn't used. More examples on how to use docstrings. Fine. Approximate counting in Emacs Lisp. Bah. No one knows Lisp is the problem. Racket language include from Lisp. Okay. What do we have? Following request. This changes only the other Racket language implementations. Oh, this is an easy merge. I don't know why this is taking so long. Change Racket lang to include from Lisp to Racket. Including algorithm. Okay, seems good. This is an easy merge. Let's go ahead and review changes. Approve. Sorry, it took me a while to get to this one. All right, let's approve that guy. Then I think we need to update the branch, and then we can merge that in. So we have that one ready to go. Stacking Hue and Crystal. Maybe it was one of these. I thought it was by. I thought someone by like Depate or something. Okay. Let's see. Let me go ahead and refresh the page. Crystal. PowerShell, Java. This is language Crystal. The code, try to try the code on systems other than Windows, you can run this. Okay, I mean, if I can't really review PowerShell, but I think that's probably okay. MRS had a few comments here. It is now approved, so it has one approval. So let's go ahead and update the branch, and I think we can go ahead and merge that guy in as well. Okay. Then what's the other one we have? Implemented Go, PowerShell, Java, GramScan, Stacking Queue and Go, Dev container for VLang, and that's kind of where, here it is. Depate. Let's see what else we have. What desktop environment are you using? I'm currently using OpenBox. It can actually be found on Discord. So here, I'll go ahead and give you guys a link. Let's do, Shadow Mishia. Let's go ahead and add first to E there. I'm giving a lot of people like, okay, so I need to ask about a little bit about the content of stream as well. 1 second. So like I've been, so for example, today I was really trying to get something done, right? And so I couldn't figure out how to do it on stream. It was one of those things where, you know, like as you're when you're in the middle of debugging, like the walls start closing in and you're like, I can't figure this out. It's impossible, blah, blah, blah. And so, you know, those are the times when I really have to close stream just to focus and figure out what the problem is. And I did that and I fixed the problem. So now I'm back streaming, you know? Okay, let's see if these guys are good to go. That one has been building. This one looks like it's ready to go. So let's go ahead and squash and merge. Confirm squash and merge. I don't like that it was co-authored by me, but that's okay. And then this guy should also be squash and merge. Out of date with base branch. Didn't I just update the branch? Update branch. Let me see what happens here. I might need to do some manual merging. Let's see what happens when, yeah, we'll see how that goes. Stacking Queue and Go, I think this one, let's see. The code is able to run with Go, stacking queue.go on in some way. We want to produce executables with the build system in construction. So I'm not sure this point is valid right now. Then you push to it. Oh, I pushed to master. I see the problem. Okay, thank you. You're totally right. I like the use of empty interface. Looks more general. I'm all for making comments in the code if there is some part of an algorithm that can be difficult to understand, but I'm not a fan of making comments describing language syntax, i.e. that T is what T is an array T in Java. Let me take a look here. Was that actually done? I don't know. Let me go back to the pull request really quick. Since PR is at Stacking Queue and Go, it looks good to me. I like the use of an empty interface to make it more general. One could think about commenting that behind the declaration. Okay, I mean, I guess I'm just gonna ask on this one as well. So what do we think? Should we, am happy to merge this one if every one else is, my current understanding is that Amaras here said we want to produce executables with the build system. Let's see, what's the thing here? The code is able to run with, doesn't, let's see. Okay, so what do we need to do to get this into the build system? Maybe I'm not clear. Interface is a language thing that makes it clear where to add your object. I think it's fine, object typing information. Yeah, okay. So let me ask about the build system then. Is this fine? Let's see, does this... I guess, let's see, what do we have here? If you know Go, you know that probably. I don't know Go. I should know Go. The code is able to run with Go. System. So I guess I'm not understanding the comment here by Amaras. Are they saying that we want to produce executables with the build system in construction? So I'm not sure this point is valid right now. I guess that's my question. Does it conflict with the current build system? Okay, so this guy is also, I think, ready to go. But let me see. 907, inconsistent approximate counting implementation. Oh, this is on me. I've been wrapping. Oh, right. For consistency with other language, maybe we should implement something less specific. A standardization of output behavior as a minimum would be a good idea. Otherwise, it might end up like 857 when more languages get implemented. Okay. So, should we just update all the languages for the approximate counting algorithm so that they output the same thing? Okay. Aborts program execution. Okay. Maybe Julia shouldn't return true or false. Julia should return... Wait, what's actually the problem here? The approximate counting algorithm currently has 4 implementations, the 4 different ways of how to act on the result of this guy. Julia returns true or false? No, it doesn't. It should... Wait, maybe I need to look at the other implementations to understand what the point is. Let me take a look at the other implementations. I might be misunderstanding. In fact, I'm pretty sure I am misunderstanding. Okay, so let's go here. Let's go to the approximate counting algorithm. Hey, Henry, how are you? And let's go to Julia. Okay, take a look at the code, and let me see actually what's happening. Scroll down here. So what does this do? Print line. It's in the test set. This guy right here at test. This guy. Okay, so let's see if we can find the issue here. No, I don't think that's the right issue. This one. Currently has 4 implementations, 4 different ways how to act on the result of this guy. So what I currently do, the test set should return pass or fail, I think. I need to double check, but it should be pass or fail. So let's take a look at the other languages. So in C, what does it do? So in C, it does assert. Okay. In C++, it prints either pass or fail. In Python, it does... what does it do? Oh, print passed. Okay. Let me see the Julia implementation, see what that does. So let's go ahead and CD into projects, algorithm archive, CD into contents, approximate counting, ls here, CD into code, Julia, ls, and now let's just run Julia. Ooh, that's a lot of .dat files. Okay. Sorry about that. It should do, the Julia approximate counting.jl. Right, so test all of them. And we get pass total. Okay, right. So the big problem here is that when we run this... Okay, actually, Henry, you're the one that created the issue. Let me ask. I only looking at the method that returns stuff and not the test stuff below. Right. So are we... Right, so here's my question to you. Are we asking... Let me run the Python code. Oh, come on. Okay, so let's do Python approximate counting.py. Python. Python. 1 second. There we go. Testing A passed, testing 12 passed, testing. Okay. I'm going to be honest in saying that the way that Julia outputs the tests is different than the way that the other languages output the tests. So because of that, I think we should have a consistent outputting pattern. Like just, okay, so my question to you is the following. Were you talking specifically about the function input and output, i.e. the line that's like here? So if return this, or if print passed, or were you talking about the overall output here? So like when you run the code, you get this in Julia, but this in Python. I got that mixed up. You get this in Python and this in Julia, right? So these should be standardized. But C will just stop program execution. Right, because it's an assert. Okay, what I can do is I can just, okay, let's create a PR right now that just fixes this. And what we'll do is we will just have it return pass or fail is what we'll do. It's not going to be super difficult. It's just return pass or fail. And I'm going to make it so Julia does not output a test set anymore. As much as I like the Julia test sets, I do recognize that for language standardization, you know, it may make things a bit more complicated. So let's go ahead and do that right now. So let's go into VI Python, approximate counting.py, move down here. Let's do if, else, print, failed. Should it just be pass and fail, or passed and failed? It's going to say testing this, so I guess it should be passed and failed, is what it should be. Okay. Let's go back into Julia. All right, let's go into VI approximate counting.jl. Let's fix that one as well. So it will no longer have the test set. So let's go ahead and remove that. Remove this. I think I can just remove these lines for X. Oh, oops, I messed that up. Print line and 8x. I'm gonna add some spaces in here just because I feel like it, and that is fine. And now in here, what we're gonna do is if, then we're going to else and end, and we're just gonna print. All right, paste in there and failed. All right, cd back into the Python version, make sure that's actually what I wrote. And it was passed and failed. Perfect. So now cd back into the C version. I think there's only 2 more languages, right? C and C++. So let's go into VI approximate counting.c. That's all fine. Assert. So here we're just going to do the same. If. Oh, okay. This is where I'm. I have forgotten how to print in C. Isn't it printf? Can't I just do passed? I think this will do, and failed. I always do stdc out. I always do stdc out in C++. All right, printf. Okay, let's see what happens. So we're gonna do g plus gcc approximate counting.c. Right. I'm an idiot. Yes. Sorry about that. That is me forgetting like the other day I forgot what STL was. Like that's how far away I am from remembering C. Gotten OOB, thank you so much for following, really appreciate it. Should work. GCC. Undefined reference to power. Okay. If f absolute value, did I do something dumb? I think I need a space here. And I think that'll do. Nope. Did this compile before? I didn't check. I assumed it did. I probably should have compiled it before. Let me do, can I do git stash dot? Okay, just git stash. All right. Oh, what? Oops. Is stdio.h included? Maybe not. Let's go into. All right, I screwed up. Let me just go back here and let me unstash because I am just stupid. Let's go back over here. Let's do git stash apply. All right. Those are the changes I want to make. Git checkout master. All right. Git status. Sure. Okay, fine. vi approximate counting.c. stdio.h is already loaded. You need math.h and probably link lm too. Okay. That might be it. GCC dash LM. There we go. /a out. Perfect. Passed. I think that's the same thing. Let me run Julia back into the Julia approximate counting.jl and see if it's the same thing. It looks the same to me. It's weird that the Julia took so much longer though. And also I have commas. Wait a minute. Oh, okay. This one did take a while. Okay, let me go back and add commas to this one. So let's go vi approximate counting.c, g, and we're just gonna add commas just because I feel like adding commas. And you guys are gonna have to deal with the fact that we have commas in the code. All right. Let me run the Python one, pi, and then approximate counting.py. Okay, that one has commas. It looks the same, I think. Okay. Thanks, by the way. I'm sorry, guys, that I've completely forgotten everything about C and C++. Like a while ago, like a few years ago, C and C++ were my preferred languages, but it's been a while. CD, C++, ls here, vi, g. Okay, so we have stdc out counting. Okay, fine. We can do it on one line. Passed and failed. Sure. That doesn't change much at all. And I think everything else is the same. So let's run G++, approximate counting, probably have a -lm as well. /a out. Okay, so it needs to be on the next line. All right, G down here. I think while I'm at it, I'm gonna add the hashtag. Or whatever it is, just to make sure that it's all correct. So we want the new line here. There, oh, there and there. And I believe that should be fine. Now, where does the hashtag go? I think it goes above this guy. Maybe? Let me see. I'm gonna double check. So what did we do for tree traversal? Where am I? Yeah, back in the tree traversal, right? There it is, tree traversal. CD code, Julia, ls here, vi tree.jl. Let me look for this guy. Let me look for this guy. Okay. It looks like it's before each. Yeah, it looks like it's before each test. So let's go ahead and do that. Back into approximate counting, ls here, cd into code, ls, cd into Julia, ls, going to vi approximate counting.jl, move down here. We no longer have the test set, but I probably should have it. Vi back into C++, approximate counting G. And so it is counting tests 100 trials. Is that even correct? Is it 100 trials? Testing. Oh, sure. 100 trials is correct. All right. Let me just grab this guy so I don't accidentally do something dumb. And then we'll do it for Julia and Python and C. Actually, let me just go ahead and put it in here for now. This, I believe, is what I need. No space. Or space. Do I need a space? I don't think I need a space. Oh. This. There. All right, let's see what that does. This guy. No such file or directory. C++. This guy, /a out. Sure. Okay, I think that's probably what we want. I mean, I'll double check, or I'll ask just to make sure, but I think this is correct. All right, cd back into Python. Vi approximate counting.py, G down here. We're gonna print passed and failed, so what I need to do this here is just add this guy. There, oh. And here. And then I want to add print. Here. Ah, there we go, perfect. There. All right, do the same for C. All right, going to vi approximate counting.c. Okay, that already looks correct. So now let's go ahead and add in the blocks. There, here, and here. All right, now finally, let's do it for Julia. Vi approximate counting.jl. Move down here. Let's just do a print line. This guy. I don't think I need the new line since it is a print line specifically. In fact, probably in Python as well, I don't need it. So let's go ahead and add in this. This, that, and that. All right, Julia, approximate counting.jl. All right, right. How do you print? Okay, that's me being dumb. Let's fix that. That, and that, this, and quit, try it again. Perfect. Okay, so now we'll do the same for Python. Python, approximate counting.py. Yes, that's what I thought was the issue. Python will take just a second. Where's my water? What did I do with it? Oh, there it is. Found it. $55 rollouts in about 5 minutes, or 15 minutes. That sounds fun. All right. I also did an error in there, so I'm adding a push-up. I think these are standardized now. Let me go back to directory, git add dot, git status. See, oh, I got the a.out files, didn't I? Git reset. Remove C a.out and remove C++ a.out. Then I think the rest of them are good if I do a git add. Status. All right, git checkout -b, and we're gonna call it prox a count standardize. Man, there is a giant something doing construction, like some sort of like I don't know, like, you know, there's like giant caterpillar devices. What are they called? Like the things with the what are these called? These giant like construction things. I can only remember the Digimon. Anyway, like there's one of those outside. Don't forget to update. Oh, from master. Yeah. Git branch really quick. Okay, ls here. Should still be good. Git status dot. Okay, git checkout a count std because I'm great at naming. -b. Okay, so you git commit -m attempt at output standardization for approximate counting. Git push origin a count std. I was about to say, don't forget to update the lines in the MD file, but there is there's just one line example, right? Thanks. So that was pushed. So let's go ahead and create the pull request, and I believe this fixes 2 issues, I think both by Henry. So I think this one, yes, so this is 909, and the other one was inconsistent 907. Perfect. Let's go ahead and create that pull request. New pull request. Oh, algorithm archive. Am I dumb? There we go. So this is an attempt to fix 907. And was also mentioned in 909. Oop. All right. Let's see. I want to assign a silent. Oh, yeah. They're not on the team, so we'll. Oh, is it about stack and queue? I'm looking at the wrong one. I'm looking at this one then? 898. 898. Sorry about that. Thank you. Yep, that's the one. Perfect. Let's create the pull request, and then the next thing I'm going to do is actually, I think, a silent tree has been putting in so much effort, and I have not. Let me go ahead and add them to the algorithm archivist as well. Algorithm archivists. And let's do invite someone, a silent tree. Oh, no. What are they on? Ice? What are they? No. What are they on GitHub? I've totally forgotten. What is their name on GitHub? Man, every time I forget what people are called. Issues, and it's going to be Storm of Ice is what it is. Here, invite someone, Storm of Ice. Yes, that's it, invite. Right, member, perfect, send invitation. Cool, okay. Let's see how that goes. Okay, in a meeting, but did that just close the reference issue? No, I don't think I did. Did I? Crap, did I do something dumb again? I don't think I did. What is the last thing I merged? I merged. Let me check. Pull request. I might have keep doing this thing where I say, oh, this is a fix for this, but it's like, no, wait. It's not a fix for that. It's just mentioned there. Let me go to closed. Partial removal. Update readme.md. JavaScript. Implement stacks and queues. What did I merge today? I don't think I closed anything. But the hope was that actually the PR that I just created will close the reference issue. So I think it should be fine. Yeah. The PR just created should close number 907, but I don't think. If I did, I'm sorry. Like, that's me. Okay. Right. So this is me. Like, I keep making the same mistake over and over again. Okay. Okay, so what I'm going to do now is I'm going to take just a quick 5-minute break. We're going to do a little bit of a workout. Looks like I've got a single push-up to do and then 55 rollouts. We'll see if I do 55 of them. We'll do a number of them. Probably not 55, but we'll see what we can do. Okay, let's go and do that now. And then we'll work on a little bit more algorithm archive work. It's currently 5 o'clock p.m. Before we do that, I think I'm going to go ahead and go over here, and I'm going to commit this to the Simuleos directory, since we do have something that's kind of working. It's actually a pretty good stopping place for the histogram for today, and then we can work on it more tomorrow. And I think that's in line with what I need to do anyway, because I'm going to have to do a lot of reading actually tonight and probably tomorrow morning before tomorrow's stream to keep going with the histogram stuff. Now that we have a basic CPU variant working, which I'm really happy about, this means that now we can move forward and we can do something hopefully even cooler starting tomorrow. Like, we can actually get some of the parallel methods in and working, which is going to be great. So go ahead and do git add histogram.jl, git commit -m, adding working CPU variant, need to deal with warp conflicts. Git push, 1 second, push origin master. Okay, the next thing I'm going to do in the next hour, so we're going to do the quick 5-minute workout, and then after we do the quick 5-minute workout, we're going to do another PR for the Euler method. A few people mentioned that there were some changes that needed to be made for the Euler method, and I'm just going to go ahead and do that. I also just realized I misspelled conflicts, but that's fine. We'll get there when we get there. Okay, let's go ahead and go over there, and then I think once we do the Euler stuff, I think that will be it for today's stream, just because, again, I've got a lot of reading and stuff to do for the histograms tomorrow, so I need to take a step out and work on that. Besides, my wife will be coming back soon, and I honestly need to go shopping and do some chores this afternoon, so that's okay. For those of you guys who were not aware, this is actually my third stream for today. I did one 1-hour stream on YouTube. I did another 1-hour stream on Twitch. This is my third 1-hour stream on Twitch. Or second 1-hour stream on Twitch today. Hopefully we'll make it 2 hours. We'll see how it goes. I realize this is awful, like genuinely awful for keeping people engaged. I get that, but also, you know, like there's only so much I can do. Like, some stuff I can't do on stream, and if I would not have taken that break an hour ago, it would have been really annoying. You sound like a superhero. Thanks. You too. Okay, I'll be right back, and we'll do the quick mini workout. Okay, looks good to me. Right, there it is. Give me 1 second. Okay, so it's one push-up and then 55 rollouts. Now look, I'm probably not doing all 55 rollouts. I'm gonna do a number of rollouts, and you guys are gonna have to deal with it. So one push-up, let's get that done first. All right, there's our one push-up. Now, should I just not do the rollouts? Maybe. No, okay, let's get it done. Let me move the camera so you can see what I'm doing. I'm not sure the best way to do that, but I think I have an idea. So I'll move this over here, and I believe that's good. Let me check. That should be fine. Okay. So I'm gonna do the rollout this way. I've got 55 of them. We're gonna see how many I do. I'll do a set of 10, maybe 15, and we'll see. So in principle, 55. Oh, hey, by the way, I'll go over here. In principle, 55 is going to be, let's see, a set of 20. Wait, 55, what is that? 15, and then 2 sets of 20. So let's do 1 set of 15, and let's see how it goes. Third stream today. Yeah, I've been in and out. I'm trying to get work done, right? And to get work done, sometimes that means I can stream for 7 hours. Sometimes it means, I can't do that. Let me see, maybe I should move this over here? It doesn't really matter, it's fine. All right. 15. Oh, yeah, and if you're, this is really stupid. If you're, sitting at a desk, you want to do some stretching, this is actually the perfect time to do so. That's actually why I think it's good to do on stream, just to take a second to focus on something else. And then to, just to get the blood flowing, do something exciting. I don't know. Anyway, give me a second. All right, let's start with 15. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Oh, I hate these. I used to love these. It was my favorite thing to do for a long time. But I suck at them now because I have not worked out regularly in a very long time. So that was 15. How many do I want to do? I know it says 55. I could technically do 55, but as you can see, I'm quite tired. Maybe I just do them. Maybe just I stop being a wimp and I just do them. Okay, 20 more. Let's go. Technically, I have 2 sets of 20 to do 55. Oh, I should have decreased the difficulty is what I should have done, but I didn't because I wanted to not wimp out. Also, I want to do one thing, and I don't know what that is. My knees are starting to hurt because this is not, it's kind of like a weird material to put your knees on. So let me move this a little bit. Okay. And let's do it again. Also, maybe there's a better camera angle? Yeah, let me try something else. Let me move this up. Oh no, oh crap. Ah, jeez. Here? And then there, maybe? What's that look like? Yeah, that's better. Alright. Alright, 20 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, almost 8, 2 more, 9. All right, last one. 10. Okay. Whew. I know you can't see me, but that was 35. I might call that. That might be what I do. 35 seems like enough. All right, I'll get back to streaming. Whew. Okay, that was way more tiring than it should have been. All this reminds me of like how incredibly unfit I am. Like, I used to be super like capable and able to do this kind of stuff all the time. Now it's just like every little movement just makes me tired. I need to get back to the days when I was like working out every day, but it's just been so long. And I suck so much right now. All right, give me a second. Okay, so for the next maybe hour or so, actually, I'm not going to do any more workouts today, so that's it for now. For the next hour or so, I'm going to work on an issue to do with the Euler method in the algorithm archive. So let's go ahead and work on that right now. And then again, that's probably it for today. After this next hour, I will have been streaming for basically 4 hours today, which, look, is not an insane amount, but at the same time, again, I'm slowly trying to ramp up my stream hours, so I don't want to overwork myself right now. So 4 hours of streaming, for a total of maybe 10 hours of working, I think is fairly reasonable. And again, I still have a few hours of reading papers after stream as well. So let's go and CD into projects, algorithm archive. Over here, we're going to do Control C, Control D, and CD into projects, algorithm archive. Okay, so the issue is in the Euler method. So it's the CD projects, CD contents, Euler method. Sorry, I think it's a forward Euler method. What? Contents. 1 second. Forward Euler method. Perfect. Make it a little bit of water because I'm quite tired. And let's get it done. So, what do we have to do? First, let's go into the Euler method chapter. Here we are. The first problem actually comes with the definition for the Taylor series expansion. So I'm actually going to do a few things. The first thing I'm going to do is just read through the chapter again. It's been years since it was written, and I do realize that I was the one that wrote it, but at the same time, like, gotta be honest, it was one of the first chapters we ever wrote. So, like, it's genuinely not, it's not great, is what I'm trying to say. So let's go to localhost. And where's the Euler method? It should be in physics solvers, I think. It's also really good to look at this right now because I'm intending to put the, Runge-Kutta methods into the algorithm archive soon. So, I think it's great to put in now. All right, let's move the forward Euler method over here so we can read it on the side. Remove the hamburger menu. Perfect. Okay, so we're going to get through this. There's a few errors, and I'm just going to talk about them as we get to them. So we're going to CD into enter. So CD into back a couple of directories and CD into contents. Forward Euler method over here. Control D. CD into projects, algorithm archive. Come on. And then we're going to CD into contents, and then forward Euler method. CD into code, Julia. LS here, over here, CD into code, Julia. And I'm going to take a look and see what the Julia code does. vi euler.jl. It should, maybe it doesn't, and maybe this is part of the issue. It checks the result, solve Euler. It only returns the Euler result, but because this was written so long ago, it doesn't actually output the result. So let's go ahead and read through the chapter and see what needs to happen. The big things that need to happen are, one, we need to update the Taylor series expansion just a little bit. There's a small notational error. But the other thing is I need to update these figures, which is going to be the big part of today, which is why I slotted a full hour to do it. It might actually take a little bit more than an hour, but the fact is I just need to get it done, right? So, let's take a look. Okay. So the Euler methods are some of the simplest methods to solve ordinary differential equations numerically. They introduce a new set of methods called the Runge-Kutta methods, which will be discussed in the near future. As a physicist, I tend to understand things through methods that I have learned before. In this case, it makes sense for me to see Euler methods as extensions of Taylor series expansions, and these expansions basically approximate functions based on their derivatives, like so. Let me take a look at the Taylor series. By the way, Linear Maze, and also Vegan AIZ. Thank you so much for following. Really appreciate it. Right. Okay. So they had an issue with my definition of the Taylor series expansion here. Okay, so here's the thing. I don't think there's actually too much of an issue with my definition of the Taylor series expansion, but someone said there was, and this is where, look, there probably is, but I don't know actually a better way to notate this. So, actually, maybe there is. So let me think about this. So usually, when you think of the Taylor series expansion, you think, I typically think of, let's see. Mr. Extreme, thank you so much for following. Really appreciate it. I'm really struggling with this. Give me a second. Let me move this over here. Perfect. Okay. So f of x is approximately equal to f of a. I didn't define what f of a is. That's my bad. Plus 1 over 1 exclamation mark and dfa over dA of x minus a, and then 1 over 2 exclamation mark d squared of df of a over d squared. So I typically think of this in terms of the kinematic equation. So x is equal to x naught, that's this guy, plus v naught t, that's that guy, and then 1/2 at squared. This is how I typically think of it. And that's 1/2 at squared. This is the jerk term after that with bt cubed and stuff like that. So in this case, it's usually t minus t naught, but people just notate it to be t, which is why I wrote it down there. And so probably what I need to do is update the Taylor series expansion. So f of x is going to be f of x naught plus d f of x over dA of x minus x naught. And so on and so forth. So I think what I'm going to do is change all the a's to x naughts. And I think that should, in principle, solve the issue. But, you know, let's not get ahead of ourselves. At first glance, I was scared that you were looking into some calculus, some Ito calculus. Oh, no. Probably not. So let's just go ahead and fix that. Because again, I think it is clear if it's x naught anyway. So let's go ahead and do that. F of x, so this is going to be x naught. And then we're going to do x naught here. Let's go down here, x naught as well. Let's see, here, there. Wait a minute. That should be x. Wait, let me think about this really quick. See, this is why I hate doing this. I genuinely, every time I do this, I get confused. Okay, let me look at this again. The problem is, like, Taylor series expansion is, like, super intuitive, but the problem is, like, notationally, it's just a mess, and it's always been a mess, and no matter, like, people, you know, they have, like, a bunch of different ways to say, like, x evaluated at this, but then it still looks ugly. Like, it's hard to explain it to someone who doesn't know the math. So, let's see, df of a over dA, where a, yeah, usually I would notate it I would usually notate it as f of xt, is what I would usually notate it as. Like I would normally say, 1 second, f of x t is going to be equal to, you know, like, x naught plus, dx by dt, of, that's also an issue, dx by dt of, 1 second, I have to think about this. Usually I think about it as, it's been a long time since I did Taylor series, man. Super long time. Okay, so v is going to be dx by dt, and then you multiply it by t in the end. But you actually multiply it by a dt. So is this going to be, it should be like t minus t naught or something. Crap. Okay, let me just look at and see what other people say. Taylor series expansion. Because clearly I just wrote a bad chapter. Okay, with notation f raised to the k. Right, I always forget. Yeah, look, don't give me that. This is exactly the notation that they use here. Okay, screw you. Like, that is identical to that notation. That's fine. All right, let me see what other people say. Download error, aborting insecure download. Okay, to be fair, Wolfram did the same thing I did. So let me try looking at this somewhere else. Taylor series, Wikipedia, okay? Let's see what Wikipedia says. So it says, The Taylor series of a real complex valued function f of x that is infinitesimally differential at a real or complex number a is the power series. I just used the same notation that everyone else did. Like, okay, fine. Like, okay. It should be x of t is equal to x at t naught. Right, x as a function of time is what it is. Right. I know I did the same thing everyone else did. Okay, let me just work on this for a second. So you're right, it's x as a function of time is going to be x as a function of t naught plus, and then it should be dx over dt of t minus t naught. Is it t minus t naught? Wait, 1 second, let me think. F as a function of, or is it just t naught? Wait. Okay, let me just do something really dumb. Usually, it's x is equal to x plus v naught t plus 1/2 a t squared. Right, that's what it is. Not, 1 second. not, who's there? Right. Okay, so x is going to be x plus v naught t plus 1/2 a t squared. Usually when I'm running this, I'll say x starts at some position, let's say 10. Then we say velocity is going to be equal to, I don't know, 10 meters per second. And then we say acceleration is going to be equal to, I don't know, negative 9.81 meters per second squared, right? And then we say after 10 seconds, so the initial condition, so then we say after 10 seconds, where are we at? So it should be t minus t naught is what it should be, because this t is going to be t minus t naught. Right. Right. Okay. So then it should be dx over dt squared, dx over dt squared of t minus t naught squared. Right. That's what it should be. I think, unless I'm completely forgetting all my basic physics, which I could be. I mean, look, I've got a PhD in the topic, but that doesn't mean I forget. I know it all. Okay, so the other issue that they had, which I'm not as willing to change on, was the fact that they didn't like how notationally, when I wrote this down, I said d over dA squared. They said that I should have this in a parentheses. Now, to be fair, it should technically be in a parentheses, but like everyone notates it that way. I've never seen anyone put a parentheses after at the bottom term. So like, let me see what they do in Wolfram. Okay, they just do f3 of a is what they do. Fn of a, where n is the derivative. Let me do someone else. Taylor series there. I mean, I guess I could look at his code. Taylor series math is fun. Now I'm looking at a slightly different notation. Okay, so I'm going to be honest in saying I actually don't think I need to update the text there. I do need to update the images, but I don't think I need to update the text. I think you got it right, but I need to add info that the derivatives are not evaluated at t is equal to t, but need to add info that the derivatives are not evaluated at t equals t naught. The derivatives are not, right. Yeah, they're fundamentally different equations, right? So are you saying that this is insinuating that, let me check. So it's x, it usually be x of t is going to be approximated as x of t naught. Okay, so to be fair, I'm getting super confused with my x's and a's here, right? So I don't think this is the clearest notation. What I could probably do is I could probably rephrase this as x as a function of t instead of f as a function of x, because again, x is, I literally use this equation later. So maybe I should do, instead of x, I should use like a and b or something. And I should notate what a and b are. No, but then I use a down here as acceleration. So this whole thing is wonky. Let's try to rephrase it with different variables so it doesn't conflict with the kinematic equation. Because I think showing the kinematic equation is nice, because I think most people will have some sort of intuition for the kinematic equation. They've probably seen it before in their physics class. Okay. So let's do, okay, what was that? I don't know. Anyway, it's probably fine. Okay, what am I gonna do next? So let's hop over here. Right, okay, I see where I am. Let's move over here. Okay, let me just quit out of here and let's think about it. Okay, so And let's go to Taylor series Wikipedia. All right, Taylor series here. Let's just scroll down. Oh, scroll up. Okay. What do they say A is in this case? So they say f of A plus f prime of A over 1 factorial x minus A. So in this case, A must be some sort of like continuous. Wait. We're evaluating it at A. So this is your T naught. So then X in this case is going to be your basically number line. So like your set of all real numbers essentially. And then we do X minus A. Oh my gosh. Look, this is stuff that I did as a high schooler and like early in undergraduate. It's stuff that like is so like I understood for such a long time. And now I'm like, oh, I've completely forgotten everything. Like genuinely forgotten everything about basic physics at this point. So let's think about this again. So f of n, f raised to the n of a of n factorial, x minus a. So it's usually t. Okay, let's write down the freaking kinematic equation. Let's get this done. Journal, new page before. Kinematic equation, x is equal to x naught plus v naught t plus 1/2 a t squared. It's usually what I write. So what is t in this case? T is going to be equal to something like 10 seconds or something. Seconds. I'm sorry, I'm really bad at this. So in that case, we have some initial location, some initial velocity, and some acceleration. That's usually what you write down for the kinematic equation. So you just plug things in. And the only reason this works is because acceleration is essentially some sort of parabolic x squared term. And then this is usually a number line, and this is normally like just like a flat constant, right? Okay. Ordon, thank you so much for following. Really appreciate it. At this point, I'm going to be happy if we can just figure out the Taylor series expansion by the end of stream today. Like, I'm just going to stream for another hour. I'm going to leave at 6 o'clock p.m. because I've got histogram stuff to do. But I think what we might do is just make sure we got the notation for Taylor series done today. And then tomorrow we'll come back and we'll fix the second part of this, which is going to be fixing the graph terms and stuff like that. So we have two parts of this, but let's just double check the Taylor series today. And I'm happy with that. Okay, so going back to understanding the Taylor series expansion. My big issue is what is A. So A is a real or complex number that you're evaluating at. So if you have some sort of function, which is going to be, it doesn't matter, it's any function, then you're evaluating it at A. So my question is, what is x minus A in this case? X minus A is going to be, I mean, it's a shift over by A, but why are you shifting over by A? Is this correcting for... Again, I always think of this in terms of physics, which is my big problem. I should not be thinking of it in terms of physics. I should be thinking about it in terms of basic mathematics. So let me look up Taylor series again. And we're going to do this on just Google. And it should pop up probably Wolfram Alpha or something. Yep. Let's see if that gives me a better definition. It's the same. It's like the same text as well. So Taylor series is a series expansion of a function about a point. A one-dimensional Taylor series expansion of a real function f of x about point x equals a is given by the following: f of x is equal to x f of a plus f prime of a of x minus a. Which is usually t minus t naught, which is to say, trying to remember how that's put in. If a equals 0, the expansion is known as the Maclaurin series, right? Yeah, so I remember this. I'm having a little bit of trouble with the intuition around how this works. The way I think about it is that it is just shifting the function with some x value. You can't always center the Taylor series around 0, right? I think x of t should replace f of x, and t naught should replace a. With x of t is equal to x of t naught plus d of t naught over dt. Should be d of x over dt. T minus T naught. I'm pretty sure it's d of x over dt because velocity is d over dx over dt. So I think it should be x of t is going to be equal to x of t naught plus d of x over d of t. Sorry, my x's and t's of t minus t naught plus d of x squared over dt squared of t minus t naught squared dot dot dot. With a 1/2 in front. Dx of dt. Dx. Wait, it's dx of t naught. Did I misread you? Oh, I did misread you. I misread you entirely. I'm sorry. Dx at t naught. You're right. You're saying you're evaluating this at t naught. Correct. Okay. Yeah. Now, does that make sense? Because usually what you do... Wait. Let me think about this. So usually, for arbitrary functions, you probably need to... Do you evaluate? I don't know if you do evaluate the derivative at... I don't know if you do evaluate the derivative at t naught, do you? I think you're evaluating it at t minus t naught. And I think this is just the creation of your new d by dx function, or d by dt function. So, like, you know, if... Gosh, I'm trying to remember the basic physics. It's been a long time. You're multiplying by t minus t naught, no? I think you're... So for the kinematic equation, you always multiply by t. I'm trying to remember why that's justified. Right, I'm trying to remember why that's justified. So you multiply by t because... Oh gosh, I really genuinely have to look up Taylor series stuff. This is so embarrassing. Taylor series examples. It's been so long. Examples, LibreText, sure. Okay. So use a formula for the coefficients. The uniqueness of the Taylor series, along with the fact that they converge around any disk around Z0, converge on any disk around Z0 with the function is analytic, allows us to use lots of computational tricks to find the series and be sure that it converges. So I can't review the Elm PR because I have genuinely no clue how to get the Elm to run. Oh, contact GA on that. GA Gillette. Gillet, I guess. He'll know. He works on Elm all the time. All the binaries are there and work. They just can't get Elm to execute. Yeah, so definitely ask GA about that. That's his... he loves Elm. So use a formula for coefficients in terms of derivatives to give the Taylor series f of z around e of z and around z naught. So since f prime of z is equal to e of z, Oh, sorry. Yep, you're right. Sorry. Okay. So we have e of z is going to be 1 plus z. So 1 is e naught plus z. Easy peasy. And then we get z, which is the derivative of... just give me the... Can I get the text? Taylor series might be here. So yeah, that's fine. I just want a... Okay, that doesn't help me. F of z is going to be z minus z naught of k. Oh, every time I have to do continuous mathematics, I just get super confused. I don't know if this is true for anyone else, but like the moment I learned that, like, you know, you don't, like, anytime we have to do anything discrete, I'm like, oh, this is easy. But then once I have to do it like continuous, I'm like, this is super confusing. I have no idea what's going on anymore. Okay, so it's going to be 1, which is going to be, what you're trying to do, is it to get a polynomial that is arbitrarily close to your original function? Right, yeah, obviously. So what you would want to do for the first coefficient is first take the value you are centering around and then add a linear factor with a multiple of the derivative and so on. Right. Right, so I understand that. That's not the issue. So I understand what the Taylor series is doing, right? Like, clearly. The issue is I'm failing to understand how you do an x minus x naught. That's what I'm failing to remember. Do you know there exist analytical functions on finite fields? Right. I mean, yeah. I mean, anyway. Right. So, give me a second. So we do 1 plus... I'm sorry, I'm being a bit condescending. I'm not intending to be. But it's just pissing me off because this is like literally high school stuff, you know? Like, it's stuff that you learn in high school. And it's like, how have I gotten this? Like, all the things to forget. This fundamental thing that's like so reliant on like nearly all of physics, I've just completely forgotten. Like, just completely forgotten. And it's just really annoying that I've dropped this far, you know? So don't worry, it's only a decline until your death, right? It's just annoying is all. I'm sorry that I'm being a bit snippy. I don't mean to be. Okay, so, right, so they get the 1 because this is going to be e raised to the 0 is 1, right? This is e raised to the z. So the next one is going to be just z, but the question is, why is that z? And why is it not... Oh, because we haven't evaluated it yet. That's why. Okay, that's totally fine. This might be why the whole t minus t naught thing might be a bit confusing then. Because maybe we... So obviously that's derivative 1, derivative 2, 3, 4, right? But the t minus t naught thing is the thing that's now confusing me. So, right, the thing that I'm confused by is the following. Why? What does this term mean? So, okay, let's just take an arbitrary function, e to the x, right? E to the x, okay? This is going to be equal to, and we're evaluating at f of z is equal to 0. So we evaluate at x equals 0. Okay, so the first one is e to 0, which is going to be the first bit. That's fine. This is going to be equal to 1. All right, the next bit is going to be the derivative of d e to the x, I guess d by dx of e to the x. So this is going to be x e to the 0. This is going to be equal to, obviously, just x. Right. But the thing I'm confused... I see what they're doing. It's x minus x naught, but x naught is 0. Okay, so we want to evaluate it at another point. So let's evaluate it at x equals 1. All right, perfect. So this is what I'm confused by. Let's just do it now. E is going to be equal to, at x equals 1. E is going to be equal to... it's going to be e of the x minus 1, where x equals 1, so it's going to be e to the 1. The next one is going to be x minus 1, x minus x naught, so it's going to be x minus 1, e to the 1. Nope, I'm an idiot. Nope, I don't understand it. This is me being stupid. Okay, so it's yep, this is me being dumb. Let me take a look at this. So the next term here is going to be e to the x over dx, and then it's going to be x minus x naught, where x naught is equal to 1. This is me forgetting notation. Okay, here's what I'm going to do, guys. I'm going to take a break. I'm just going to figure this out outside of stream because this is just frankly embarrassing is what this is. So I'm just going to do it off the stream. And then I'll do some reading for the histogram stuff. We'll come back tomorrow, fix up the plots. I'm just going to get this done outside of stream and go from there. I am so sorry that I'm just like, it's just stupidly embarrassing is what this is. So I'll be back tomorrow. I might just missing what you're saying, but the whole difference is that you can define g of z is equal to f of z minus z naught, and then taking the expansion of g of z around 0, then just reintroducing f again. The reason you can do this is because the derivative of z minus z naught according to z is 1. Yeah. Anyway, I'm just going to have to figure it out. Thanks, guys. I'll talk to you later. Bye, guys.